Okay, let's start this. Restricting domains of functions to make them invertible. Let's check this out.
To which intervals could we restrict f of x is equal to cosine of x minus pi over 4 so that f of x is invertible? And they show us what cosine of x minus pi over 4, what it looks like, the graph of it. So let's just think about what it means for a function to be invertible. So a function is a mapping from a set of elements that we would call the domain. So my pen is a little off today, so let's see if it works okay. So this right over here is our domain. And this over here is our range. Our range. And a function maps from an element in our domain to an element in our range. That's what a function does. Now the inverse of the function maps from that element in the range to the element in the domain. So that over there would be f inverse. So that's the direction of the function. That's the direction of f inverse. Now a function is not invertible. One of the situations in which a function is not invertible, you could have a function where two elements of the domain map to the same element of the range. So both of these elements map to that element of the range. So both of these are the function. But then if this is the case, you're not going to be able to create a function that maps the other way, because if you input this into the inverse function, where do you go? Do you go to that element of the domain, or do you go to that element right over there? And so one way to think about it is you need a one-to-one mapping. For each element of the domain range, there's only one element of the domain that gets you there. Or another way to think about it, you could try to draw a horizontal line on the graph of the function and see if it crosses through the function more than once. And you can see that this is indeed the case for this function right over here. If I did a horizontal line right over here. Now why is this the issue? Well, this is showing us, actually let me do a number that's a little bit easier to look at. So let's say I drew the horizontal line right over here. Now why is this horizontal line an issue? Well, it's showing us that just even what the part of the domain that's being graphed here, that there's several points that map to the same element of the range. They're mapping to 0.5. 0.5. If you this value right over here, when you input f of that is equal to 0.5, f of this right over here is equal to 0.5, f of this right over here is 0.5. So if you have multiple elements of your domain mapping to the same element of the range, then the function will not be invertible for that domain. So really what we're going to do is we're going to try to restrict the domain so that for that domain, if I were to essentially apply this, what I'd call the horizontal line test, I'd only intersect the function once. So let's look at the graph of the function once. So let's look at these choices. So the first one is an open set from negative 5 pi over 4, negative 5 pi over 4. So that's negative pi and another fourth of pi. So that's, I think, starting right over here, going all the way to negative 1/4 pi. So that's this domain right over here. Let me do this in a new color. So that's this. And this does not include the two endpoints. So here, I can still apply the horizontal line, and in that domain, I can show that there's two members of the domain that are mapping to the same element in the range. And so if I'm trying to construct the inverse of
What are
that,
you trying to do?
what would this which is I guess is negative 0.6, what would that f inverse of negative 0.6 be? Would it be this value here, or would it be this value here? So I would rule this one out. So let's see, negative pi to pi. So negative pi to pi, I'll do this in this color right over here. Negative pi to pi. So once again, this is a close, so we're including the two boundaries. We're including negative pi and pi in the domain. But once again, over that interval, I could apply my horizontal line here, and notice, well, actually I could even apply the original one that I did in blue, and notice there's multiple elements in the domain that map to, say, 0.5. So what would f inverse of 0.5 be? You can't construct a function where it maps only to one element of the domain. So we could rule this one out right as well. Now, negative 1/2 pi to positive 1/2 pi. So negative 1/2 pi, so I'm running out of colors. So negative 1/2 pi to positive 1/2 pi. This one is interesting. If I apply a horizontal line there, there, so let's see. But if I apply a horizontal line right over here, I do intersect the function twice. So I have two members of this domain mapping to the same element of the range. So I can rule that one out as well. And I'm left with one last choice, so I'm hoping this one will work out. So 1/2 pi, so it's an open set, so 1/2 pi, right over there, to 5 pi over 4. 5 pi over 4. So that's pi and another 1/4. So that's right over there. And let's see. This is, if I were to look at the graph here, it seems like it would pass the horizontal line test. At any point here, I can make a horizontal line over that domain. Actually, let me do it for the whole domain. So you see that for the whole domain. And I'm only intersecting the function once. So for every element of the range that we're mapping to, there's only one element in our domain that is mapping to it. It's passing our horizontal line test. So I would check this one right over there. To which intervals could we restrict f of x is equal to cosine of x minus pi over 4, so that f of x is one element of the domain that gets you there. Or another way to think about it, you could try to draw a horizontal line on the graph of the function and see if it crosses through the function more than once. And you could see that this is indeed the case. To which intervals could we restrict f of x is equal to cosine of x minus pi over 4, so that f of x is invertible? And they show us what cosine of x minus pi over 4, what it looks like, the graph of it. So let's just think about what it means for a function to be invertible. So a function is a mapping from these are the functions there. So let's say I do the horizontal line right over here. The function will not be invertible forever. But once 1/2 pi to positive 1/2 pi, this one is interesting. If I apply a horizontal line there.
Okay, restrict. Okay, fake function f graphed below is not an invertible function. Okay, here it can. To which intervals we can restrict the domain of f to make an invertible? X is bigger than 1 and less than 6. X is bigger than 1 and less than 6 here. Checks out. So I guess so. X is bigger than 0 and less than 8. Bigger than 0 and less than 8. Yep. So minus 4, minus 8 to minus 4, minus 8 is here to minus 4. Okay. It's not an invertible. To which intervals we can restrict them? Minus 8 to 1, from minus 8 to 1. Nope. 3 to 6. 3 to 6. Check, check. Check, 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 check. Nope. 2 to 5. 2 to 5. check, 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 check. Yep, 25. Okay. -6 to -2, -6 to -2. I don't think so. 3 to 5. 3 to 5. Check, 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 check. I have to go 3 to 5. -2 to 2. I don't think so. 2 check, 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 check. Check, 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 check. Yep, just here. -6 to -2. -6 to -2. Check, 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 check. Then vertical quadratic. X is less than 0. Here. Check, 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 check. Check, 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 check. Yep. S -4 to 4. Wrong. Here it touches. X is larger than 0. Check, check, check here. X is larger than 0. Next, lesson 4. Reading inverse values. Okay, should we continue? I think we should. Let's do this.
We're told the following graph shows y is equal to f of x, all right? And then the first question they say is, what appears to be the value of f inverse of 2? Pause the video and see if you can have a go at that.
Y f x. So I got y of x. So I got x is 6. I got 2. Am I correct? 1 something. I got 2. I got 3. Yeah. So sketch the graph of. It's gonna be from where? From here. Am I correct? Wait, the inverse. The inverse is gonna be if x is 2. No, I think it's here. If x is 2, it's gonna give me 3. Am I correct? So the inverse is gonna be if x is 3, it's gonna give me the inverse is if x is 3, it's gonna give me 2. So if x is 3, it's gonna give me 2 here. I guess. So it's gonna be something like this. I would say.
All right, now let's work through this together. So it's important to realize they're not asking us what f of 2 is.
F inverse 2. So this is 3, so that's 2. 2, f inverse 2. F inverse 2. If this is 3, it's gonna give me 2. F inverse. So wait. I gotta go to 2. What is it? 2. What is it? 5, 2 is 5. So 5 gives me 2, 2 gives me 5.
They're asking us f inverse of 2. F of 2, we would say, okay, when x is equal to 2, that's the input into our function, and then the graph tells us that f of 2, it looks like it might be a little bit more than 2.5, maybe it's approximately 2.6. But that's not what they're asking us. They're asking us f inverse of 2. And just as a reminder what an inverse function is, if we have some input x, and we input into our function f, that into f inverse, so we are part of this chain of inputs and outputs. We're saying we want to figure out what f inverse of 2 is. So this part right over here is going to be equal to 2. So we're saying when f of x is equal to 2, what is the corresponding x? So when f of x is equal to 2, what is the corresponding x? We get 4. So let's write that down. F inverse of 2 is equal to 4. So when x is equal to 4, you input that. F of 4 is equal to 2, or f inverse of 2 is equal to 4. Now the next part, they say sketch the graph of y is equal to f inverse of x. So an important thing to realize is of a, which implies that the point a comma b is on the graph of f. Then we're dealing with f inverse. Think about swapping these two, the a and the b's here, which means the point that's on our original graph f, if you swap the x and the y, that's going to be on our f inverse. So let's just pick some points. And once again, they're just saying sketch, so it doesn't have to be perfect. So if we look at this point right over here, that looks like the point negative 10 means if we 4 on the graph of f inverse. Let's say this point here. This 2 comma 3 comma negative 2, this point right over here, 2 comma, it's like roughly 9, little, maybe let's just call it 9, negative 10, maybe it's 9.1, negative 10. Negative 10, 9.1 would be on the inverse.
Just
Negative
sketch.
10, 9.1 right over there. And so then we can connect the dots to try to sketch out what the inverse function is going to look like, the graph of the inverse function. So it's going to look something like that. And you might notice it looks like it's a reflection about the line y equals x. It looks like it's a reflection about that line, which is exactly right.
Okay.
We're told the following table shows a few inputs and outputs of function g. All right, we have some possible inputs here for x. And before we work that function, take this.
Okay. If inverse 54 gives me 62, so 54 gives me 65.
What was the output of g of x? That is actually back to our original input right over here. So what we're focused on right over here is g inverse of 54. So we can think about this part of this little chain that we set up. So what we're inputting into this inverse function is 50.
Look, man, g of x, what is x? G of x, 54 gives me 62. Right? Okay. Now, g inverse is g of 62. So I got no 62 here. So it's gonna be no. G of 54 gives me, okay, G inverse 54. I guess here, 65. Anyway,
Before. So
right, so
what we want to say is, all right, when g of x is equal to 54, what is x? And we can see that right over here, when g of x is 54, the corresponding input, original input, one way to think about it, is 62. So this will be equal to 62.
Wait, that's inverse.
Now, some of you might have been tempted to say, okay, look, it looks like I'm inputting a 54 into a function. So I'll say, okay, x is the input. Let me just go to 54 right over there as the input. But remember, this 54 isn't an input into the inverse of g. This is an input into g of x. So if you wanted to evaluate this, if you wanted to evaluate g of 54, then you would look at the 54 up here and say, okay, that's going to be equal to 65. But we're looking at the inverse of g. So one way to think about it is, when 54 is the output in g, what is going to be the input? And we see that that is 62.
Okay. So there should be an inverse. Okay. Okay. Let's do this. Gradient, mx, which of the following shows the graph of y mx inverse x. Choose the answer. Okay. Now, at -7, we got 0. So, which tells us at 0, we get -7 here. So, yeah, it's gonna be here. So it must go through 7. That's 1, 7, and I got the regular one is if 6 is the inverse. Let's check this out. If 6, where does 6 go? 6 here, where does it go? In this graph, 6 goes to 8. So the inverse is when it's gonna be 8, it's gonna go it's gonna go 6. 6 here. So when this is gonna be 6, where is it gonna be? Six, 6. Said that when -7 is 0, therefore when it's 0, it's a -7. It's a -7 here. Okay, so it's gonna go through 7. That's correct. Now, when it's -6, it's gonna be, I don't know, 2. So when it's 2, it's gonna go -6 here, here. So Yeah, minus 6. So all the way to when it's gonna be 0. When it's 0, it's 6. So when it's 6, it's gonna be 0. When it's 6, it should be, no, when it's 6, it should be 0. Wait, when it's minus 6, wait. When it's 0, it's 6. So here, when it's 6, it's 0. 6 is 0. It is 0. Look, it's going nowhere, so it is on the 0. So that's correct. So what else? If it's 2, it is, let's say, 6. So when it's 6, it's a 2. It's a 2. It's a here. So when it's 6, right? When it's 2 here, it's 7. 7. So when it's 7, it's a 6. It's a 2. It's a 2. It's 2 here. So it should be, this is a 2. And then we got, when it's an 8, it's a, I don't know, 7. So when it's a 7, when it's a 7, it's a 8. So when it's a 7, no, when it's an 8, it's a, yep, I would go with this one. I don't think so. That'd be easy. Check the other graphs. The following graphs shows function. What's the value of minus 1? So G, okay, the inverse of minus 1. So I got, hold on, this is got, again, what do I have? I have 1, this is confusing. Alright, let's go. What does give me, which one gives me minus 1? It's a 5. So 5 gives me minus 1. What does 1 give me? 5. 5. Okay. Okay. So HG F9. So I got 9, 37. So 9, I got 9. What am I looking for? What does 9 give me? 37. It does give me 30. Because that's the inverse. Fetch X 37. 9 give me minus 6. 9 here gives me 37. So we got 37. Last but not least, no, just kidding. Which of the following shows the graph of y minus 1 inverse? So I got 0 at 4, therefore it would be 4 at 0. So here it should be, nope, no, no, no. Yeah, 4, check this out. 4 is 0, is 0. Okay. Should we finish this unit? I think we should. Oh my god, this is all? Well, like fuck sad. Fuck sad. Terrible fun. Seriously. Fucking deer. Give a fuck about them deer. Honestly. For real. My deer is elsewhere than Saudi Arabia. I don't give a fuck about Saudi Arabia. By verifying inverse functions from tables, you get 4 minutes. Shut the fuck up.
So the following tables give all of the input-output pairs for the functions s and t. So we see this first table here, we have some x's, and then they tell us what the corresponding s of x is. And then in this table, then we have some x's, and they tell us the corresponding t of x. It says complete the table for the composite function s of t of x. We want to fill in these 5 entries here. And then they ask us, are s and t inverses? So pause this video and see if you can figure this out on your own before we work through it together. All right, now let's work through this together.
So, our functions s and t inverses. S and t inverses. What are you talking about? S and t. Are they complete the table for the composite function s? Don't forget. The following tables give all of the input-output pairs for the functions s and t. Okay. Complete the table for the composite function. We get that. So tx, what are we having? And then we have this r, s, and t inverses. R, s, and t inverses. So we got x minus 5 is 100. So minus 5 here is 100. That's an inverse. And I got minus 112, minus 112 inverse. And I got, wait, t. This should be t. Wait, this is t. Okay. 218. So I got no 18 here. So
let's just
wait. 2 is 18. I got no 18 here. So What do I have? 70, or is it this one? So let's repeat. Minus 5 equal 100. 100 equal minus 5. Minus 1 equal 12. 12 equal minus 1. 2 equal 18. 18 equal 2. 7 equal 70. 70 equal 7. 8 equal 61. 61 equal 8. So it's an inverse. It is an inverse.
Remind ourselves what's going on with a composite function like this. So you're going to take some x value, and it looks like we're first going to put it into the function t.
Just need
That is going to output t of x, and then we're going to take that output, take that t of x, and then it will be the input into s.
what do we
And
get?
then we're going to input that into
12.
s, and then that would output s
12
of
minus
what we
1
inputted, which in this case is t of x.
minus 1
So
equal
let's go on that journey. So what we're going to do is first take these
12,
values, put them
18,
into
61,
the function
71,
t, figure out, all right, 1 over
100.
that
Okay,
of
it's an inverse.
bracket of function s, the inputs, that is
It's an
functions
inverse.
are inverses.
Inverses. Okay.
In this video, we're going to think about function inverses a little bit more, or whether functions are inverses of each other. And specifically, we're going to think about, can we tell that by essentially looking at a few inputs for the functions and a few outputs. So, for example, let's say we have f of x is equal to x squared plus 3. And let's say that g of x is equal to the square root, the principal root of x minus 3. Pause this video and think about whether f and g are inverses of each other.
Okay. We're going to have to go f of gx equal this one. So equal x. So f of gx, wait, this must go with this. So it's not because of the square root. It's going to be x squared plus. Okay, so it's not. You know why? Because it's going to be equal to x. Look, x squared plus 3, if we plug it here in the x, plus 3 and minus 3 is going to cancel each other. Left with x squared. X squared, the square is going to go with the square root and left with x. So is that an inverse? Not an inverse. You know why? Because it doesn't equal this one. It doesn't equal, what did we say beforehand? It's gonna equal each other. The inverses before, what was it? The
Alright, now one approach is to try out some values. So, for example, let me make a little table here for f. So this is x, and then this would be f of x. And then let me do the same thing for g. So we have x, and then we have g of x. Now, first let's try a simple value. If we try out the value 1, what is f of 1? Well, it's going to be 1 squared plus 3. That's 1 plus 3. That is 4. So if g is an inverse of f, then if I input 4 here, I should get 1. Now that would prove that they're inverses, but if it is an inverse, we should at least be able to get that. So let's see if that's true. So if we take 4 here, 4 minus 3 is 1. The principal root of that is 1. So that's looking pretty good. Let's try one more value here. Let's try 2. 2 squared plus 3 is 7. Now let's try out 7 here. 7 minus 3 is 4. The principal root of that is 2. So far it is looking pretty good. But then what happens if we try a negative value? Pause the video and think about that. So let's do that. Let me put a negative 2 right over here. Now if I have negative 2 squared, that's positive 4 plus 3 is 7, so I have 7 here. But we already know that when we input 7 into g, we don't get negative 2, we get 2. In fact, there's no way to get negative 2 out of this function right over here. So we have just found a case, and frankly any negative number that you try to use would be a case where you can show that these are not inverses of each other. Not inverses. So you actually can use specific points to determine that two functions like this, especially functions that are defined over really an infinite number of values, these are continuous functions, that using specific points, but you actually can inverses, because there's no way that h of x, really simple functions, h of x is equal to 4x, and let's say that j of x is equal to x over 4. We know that these are inverses of each other. We'll prove it in other ways in future videos, but you can't try every single input here and other than just looking at specific.
Let's see, 4x over, if we plug it here, the 4x, what is it going to give us? 4x over 4x over 4. The 4 is going to go with the 4. I'm left with x. Still left with x.
The values to prove that two functions are inverses of each other, although you can use specific values to prove that they are not inverses.
Let's verifying inverse functions.
Let's say that f of x is equal to root of, see what I get. I encourage you, like always, pause the video. 7 to the third power minus 1. Notice, we're at x plus 1 to the third power to just be equal to x. The cube root of, and actually let me write it out. Wherever I see an x, I can write f of x instead. I didn't do it that last time. I went directly and replaced with the definition of f of x. But just to make it clear what I'm doing. So everywhere I'm seeing an x, I replace it with an f of x. So the cube root of f of x plus 1 minus 7. The 7? Lucky for us, this subtracting 1 and adding 1, those cancel out. And so we're going to take the cube root of x plus 7 to the third power. Interesting. F of g of x is just x, and g of f of x is x. So if we, in this case, if we start, put x into f of, put x into the function possible inputs to this value is f of x first, f of x, I should say, g of f. We're applying the function g to the value f of x. And so since we get a round trip either way, we know that the functions g and f are inverses of each other. In fact, we can write that it is equal to the inverse. Of f of x. Inverse of, let's say that f of x is equal to 2x minus 3, and g of x is equal to 1/2 x plus 3. What I want to do in this video is evaluate what f of g of x is, and then I want to evaluate what g of f of x is. So first I want to evaluate f of g of x, and then I'm going to evaluate the other way around. I'm going to evaluate g of f of x. But let's evaluate f of g of x.
What are you talking about? Are we still talking about inverses, verifying inverse functions by composition, not inverse. By composition inverse. So this is,
like always, I encourage you to pause the video and see if you can work equal to our input instead of f of x. So let's say g of f of x. And we also didn't do a round trip. We didn't go back. F of x does not equal the inverse of g of x. Does not equal the inverse of g of x. And we write over to it. We did not get back to the same place. We didn't get back to x, we got back to x plus 3. Same thing over here. We see that we did not get back to x, we got back to, or we got to x plus 3 halves. So they're definitely not inverses.
Okay, I think we're into something. The article includes inverse functions, the most let's take function f and g, for example, f and g of x 3x minus 1. MBS can suck it. Let's take functions f and g, for example, f of x, okay, and g of x. Notice f and g2 equal. Please show me the calculation. Okay, here's what we get. Follow up. The inverse composition, x for all the domains. Example 1. Okay. Example functions f and g are not inverse. Okay, check your understanding. In general, check if we can compose them if the result x is x. Functions are inverse, otherwise they are not. If to check f and g are inverse functions, we can compose them if the result is x. The functions are inverses, otherwise they are not. I don't think so. So it's talking about the same thing here. It's talking about the same formula. Yep. So it got to x here. Doesn't equal x and equal x. Okay. Write simplified expressions of x in terms of x. So what do we have? Fuck you and fuck your scholarships. Hey. I'm a one-man army. Wait. No. X equal 2x plus 7 h of x equal x minus 7 over 2. Right, simplified f of h of x. F of h of x. So we go to x minus 7 over 2 plus 7. So what are we having here? 2 goes with the 2. I'm left, and minus 7 goes with the plus 7. So this is equal x. Okay. And I got h of f of x equal, I got 2x plus 7 minus 7 over 2. So what do I have? Plus 7 goes with minus 7. Am I correct? And there is left 2x over 2. Of course, it's all over 2, so does it? This is I guess it's equal x. So x, x, yes, check. Okay. Fuck off, fuck off. F of x equal 4x plus 10. And I got g of x equal 1/4 of x minus 10. So I got f of g of x equal, I got 4 over 1/4 x minus 10 plus 10. So as I said, this will go with this, I'm left with 1x, and this will go with this, I'm left with x, and then here we'll go g of f of x. Is this the same? I got 1/4 of 4x plus 10 minus 10 here. So yep, so this is actually over 1. So but seriously, isn't this gonna, wait, how do you do this before? Seriously? Wait, 2, yeah, it's not the same. It made me get confused. So not the same, because here I'm gonna have to distribute it. So what's gonna happen? Look at it. 4x plus 10 minus 10. This is gonna have to be distributed. So what's gonna happen is this is gonna be x plus 10 over 4 minus 10, which gonna give me, I don't know how to do this. This is over 1. Check, check, check. So I got 10 minus 40 over 4, get minus 30 over 4. I guess x is gonna be 30 minus 4. Am I correct in the math? Let me check it out. 10, wait, 10 over 4 minus 10. Wait, 10. Actually, it's 15 over 2. Why? It is correct. But what he did here, it's minus 15 over 2 because he simplified. And what he did is took this 30 divided by 2, which can give me x minus 15 over 2. So it's not equal. I got x. What is this? F of g of x. F of g of x, I got x. And here I got x minus, let's say 7.5. No need for trouble. Nope. Check. Real. Wait. What is this? G f of x. So what are you saying? Are you saying it's the same? Minus 15 over 2. Are you saying this is equal x? This is equal x? Yes. It's wrong, I know. So what's happening? Here 4x plus 10. It's a no, definitely no. And here it's a minus 7.5. So here's the problem. What did we do wrong here? Yep, it's not x. See where we went wrong? This over here, so it's x minus 40 plus 10. So it's x minus 30. X minus 30. Okay. Give me a new paper. What are we having? Write simplified expressions for f h of x and h f of x in terms of x. I get f of hx, so I got 2 over 3 and 2 over 3, and I got here I'm gonna plug in the x, hx, which is 3 over 2 multiplied by x plus 8 minus 8. So it's an x. Seriously, now this time, because this is gonna have to be, this is multiplied and all of this, so this is gonna cancel this and this is gonna cancel this. So I'm left with this, which is this is gonna cancel this x. Okay. Next, h says 3 over 2 multiplied 2 over 3 x minus 8, and we got plus 8 here. It's not gonna be the same because this has to be multiplied here and here. So what are we gonna left of? 3 over 8 over 2 over 3x minus 8 plus 3 over 2 multiplied by 8. So what are we having? We get x and minus, we got x and minus, it is the same, 3 over 2 multiplied by 8 and plus 3 over 2 multiplied by 8. So this This will cancel this. I'm left with x. It is the same here, so here x, x, yes, check, correct. Thank you very much. Let's do the exercises. What are we at? Oh my god, are we still left? We got ready to practice. Let's do some practice. Give me a new paper. Functions f and g are invertible functions. F, okay, and g. Answer two questions about this. Write simplified of f(g)(x) in terms of x. Are functions e and g and inverse? We have to answer the two questions. So we're gonna go f of g of x which means 4 multiplied in 1/4 x plus 3 minus 3, but this is gonna be not the same. Well, this is gonna have to be go here and here, so I got x plus 12 minus 3, and I got x plus, what are we having? That's a 9. That's a 9. So that's a 9. Reverse it. So I got this x plus 9. Let's reverse it. I got 1/4 over 4x minus 3 plus 3. So what's gonna happen is this is gonna be multiplied here and here. So we're gonna have x minus 3 over 4 plus 3. It's not the same. It's not an inverse. Because minus 3 and 1, okay. Minus 3 and plus, what do I have? Check, check, check. I got minus, oh wait, 3, minus 3 of 1. That's a minus 3. And 4, 3 of 4, 3 multiplied by 4, that's a plus 12 over 4. So I get minus 3 plus 12, which is equal 9 over 4, which is equal nothing. I really can't do anything about it. 9 over 4, so it's not an inverse. No. Check. Okay. Answer the 3 questions about these functions. Value. What's the value of h2? h2 here. 4 plus 5, 9. No, f of h2. So I got 9. 9 plug it here. That's 3 minus 1. That's 2. So I got 2 here. H of f of 16. So I got 16. That's a 4 minus 1. That's a 3. 3 square. 3 square is 9. Plus 5 is 14. 14. Let's go 14. So based on the previous compositions, is it possible that f and h are inverses? Because of the minus, we'd say. Because of the minus? No, we'd say no. You know why? What did we take? 16. Put it here. And we got 4 minus 1, that's a 3. 3 squared, that's a 9, plus 5. But what if we take minus, that's gonna be, what do we call it? Is it called, what do we call it? I don't know. It's gonna be number, something numbers. I forgot. Sure, I have it here somewhere. Somewhere in my, okay, wait. In my math, my college math, I did a college math. My college math in, I don't know, 2 years ago. Was part of my civil engineering study at my college, and I was explaining it to my fellow colleagues. So what I have, what do I have? Videos. الأعداد المركبة. What is it? الأعداد المركبة. Complex numbers. That's gonna be a complex number. Look at it, complex numbers. So this is, I did all this, you guys. Look at my channel, but that was in Arabic before I take it to another level, which is English. So that's gonna be a complex number. Nope, I would say no, but seriously, I can't tell by these two composites. But if we take here, it's never gonna be minus. You know what I mean? It's not gonna be minus. But what if we take here minus? It's gonna be complex number. A complex number, I don't know. Should we take this? Should we do this? Is it possible that f and h are inverses? I would say no, but I'm gonna take it to practical steps, which is, let's say, x squared plus 5 minus 1 and x is 1 all squared plus 5. What do we have? How can we do this? Look, this I can't get rid of these two. I can't get rid of the square root because of the plus 5 here. So what am I gonna do about that? It's not an inverse. I don't believe it's an inverse. It's gonna be square minus 2 over x and 1 plus 1, which is gonna be x minus 2 plus 1. Now, What can we do with this? I don't know. It's not the same. I don't know what can we do here. Can we square both sides? Can we square this and this? I don't think we, because it's not two sides. So what are we gonna do here? To call this squared. What is it gonna be? It's gonna be equal. X squared plus 5 squared minus 2 x squared plus 5 and 1 and plus 1. It's going to be squared, but it's plus 1. Okay, so what are we having? Okay, so we have x squared plus 5 minus 2 x squared plus 5 plus 1. Is it the same as this? I don't think so, no. So it's not an inverse. Okay. Following tables give all of the input-output pairs for the functions s and t. For the functions s and t, so I got s and t. Okay, complete the table for the composition function stx. So we have s over tx. So 44, plug it to t, so I got 44, that's minus 10, and I got minus 10, that's 44. So 44. And I got 52, minus 4, minus 4, 52. Okay. 70, I got 70 to 2 to 70, 70. Wait. I got, yep, I got 70 here, 2, that's 70, so I got 70. R, yes. Okay, functions g and h are invertible functions. Answer two questions. Write simplified function for hgx in terms of x. hgx, I got this. Okay, so hgx. So this the cube will go with the cubic root. So what am I left with? X minus 1 plus 1. That's an x. Our functions, you just said are invertible functions. What do you mean, are they inverses? Yes, they are. You said it. Wait. Okay. Going back to cube. He said are invertible functions. Functions g and h. And then he says g and h are inverses. Well, we're gonna have to put it into tests. So this is went to x, and I got over 3 plus 1 all. Oh my god. All minus 1 all over 3. So what I have? Well, first, Let's be honest. We can go the long road. But actually, what we can do is we can just just this will go with this, left by this, this will go with this. It is an inverse. X. It's an inverse. Yes. Thank you very much, baby. We finished. Up next article. I think we're finished with Unit 1. Why do we need to know how to compose? Composing functions allow us to combine two or more functions into one. We can do this technique to build more complicated functions from simpler ones. It also allows us to model more complex situations in math, physics, engineering, and other disciplines. Allows us to model more complex situations in math, physics, engineering, and other disciplines. What is an invertible function? An invertible is one that can be undone or reversed. That can be undone or reversed. In other words, we can find another function that will take us back to where we started. For example, a function that adds 2 to a number is invertible. To a numbers that adds a function that adds 2 to a number is invertible. The inverse function would subtract 2 from a number. Why do we sometimes need to restrict the domain of a function to make it invertible? In general, we do not always need to restrict the domain of function to make it invertible. However, there are certain cases where it's necessary. To be invertible, a function must have the property that each input maps to unique output. Otherwise, the inverse function won't be able to undo the original function unambiguously. For example, in the function f(x) equal x squared, both -2 and 2 map to 4. Should the inverse function map 4 back to 2 or ambiguous, but a function can only have one output for a given. However, if we restrict the domain f to x larger than 0, non-negative numbers, then the function becomes invertible. How do we graph inverse functions? The easiest way to graph an inverse function is by reflecting the original function across line y, x. This is because the input and output switch places when we invert function. Where are composite and inverse functions used in real world? These functions are used in a lot of places. For example, in physics, we might use composite functions to model the motion of a failing object. In economics, we might use an inverse function to model the relationship between supply and demand. Quiz 2. Let's do quiz 2. Time for quiz. Already proficient or master, or you are already a proficient or a master of these. There are no more levels to reach. So what should we skip it? What does that mean? What does that mean? Should we skip it? If is a finite function, wait, can we skip it? Level up on the above skills and collect up and collect up to 0 mastery points. Unit test, level up on all skills in this unit and collect up to 160 mastery point. Okay, start unit test. 10 to 20 minutes, 10 questions. Well, perhaps, did you? So, what do we say? Unit test, leave it in a video by its own. Okay, I'm gonna take a little break. Sorry. What do we say, guys? Fuck you. Always. Back in the Middle East. Let's do this. The following graph shows function f. Okay? It's the value of 6. So we get 6. 6 is I don't know, 5. F inverse. So I got 6. Gets me here. So what do I have? Is this 6? I don't think it's a 6. 6 equal 4. I got 6 equal 4. 6 equal 4. So what does 4 equal? What does 4 equal? I got 6 equal 4. What does 4 equal? It's 6. F of 6 equal 4. So I get 4, 4 equal 6 also. So what does that mean? Very weird. Which means that's not the inverse of 6. Gotta go somewhere where it's 6. I got 6. Yeah. 3 is equal 6. So what's gonna be? Over the y-axis. If we take it over the y-axis, it's gonna be, I take it here. So 6 to 4. That's 4 to 6. That's 4. That's 6 to 4. Which means the inverse is 4 to 6. Okay? So I got, what do I need is 3 to 6. I got the inverse of 6 is 3. It's 3 here. Here. So it's gonna be like this. I reckon. I'm gonna go with 3. Fucking Anis, a math teacher, noticed that the average grade G on an exam giving that n students watch the related video can be given by the function G of n equal 50 plus. Okay. Relating by the function, she also noticed that the number S of students who watch an m-minute video can be modeled by the function Sm equal 30 minus m, which expression gives the average grade on an exam if the related video is m minutes. So wait. G, wait. Notice that the average grade G on an exam giving that n students watch the related video can be given by the function. So n students, number of students, This is the G average, number of students, and he wants it, which expression gives the average grade, which is the G, the average grade on an exam if the related video is in M minutes. So I got SM. So GSM. GSM, which means I'm gonna plug this here in the end. So I got 50 plus 1.5 multiplied by 30 minus 1.5 m. So I got here 1 minus 1.5 m minus 1.5 m. So it could be this or this. It cannot be this. But what are we having here? I got 50 plus 1.5 multiplied by 30. That's 45. So I am here. This one. Okay. Okay, functions f and h are invertible functions. Fuck off, man. Functions f and h are invertible functions. fx x cubed over 27 and hx 27 multiplied by the cubic root of x are two questions about these functions. Try to simplify the expression for h f of x in terms of x. hfx. I got this one, fx plugged here. So what do I have? No, I can't do that. Can I? $27, yes I can. Can I? The square root of 27. What is the square root of 27? The Yep. No. Square root of 27. 3. That's 3. So do you wanna see how this is gonna work? So this is how it works. This is how I'm gonna do it. I got 27, the cube root of x over 3 over 27, and that's it. Okay, so what I'm having is 27, the cube root of x over 3 over 27. Oh, sorry, 3 over 3. Let's do it. Let's check this. So actually this will go this, and I'm left with 27 x cubed over 3, and that is what? That is a 3. not really. 27 over 3, not 3 over 3. That's actually, I think it's a 9. Am I correct? What is that? So I'm going to multiply it in 3. So that 3 goes with 3. What am I going to have? Wait. 27. That's 9. Okay. 3 over 27. That's a 27. But that's going to be so fucking ridiculous. This one. Over 3, that's 9. Let's go with this. So what am I left with? I don't think so. I think I'm going to go with 27 over 3 makes 3. Are they inverse? I'm going to have to check it the other way around, which is 27. Wait, where did I get this from? 27. Oh, cube over 27. Man, why are you making this so difficult? So 27 and 27 and 27. It's not, it's the same. It's multiplication, and I get, which is it's not the same. It's not an inverse, and this is gonna be, it's gonna go, it's gonna get to, I don't know. I don't know. What did we reach? Where do we went? 27x squared over 3. 27 27x square. Nope, not an inverse. Fuck off. I got no other way. Give it another try. Where are we going? Where did we start? $27. Okay, so I got lost. The graphs of the equations y f x and y h x are shown in the graph. Which of the following best approximates the value of f h2? So I got h2, h2 is, let's say, minus 1.5. So minus 1.5, that's 6, minus 6. Okay, evaluate. Minus 11. Are you for real? So I got G 14 minus 11. That's 25. That's 5. 5 and 3, 15. Minus 8. That's 7. Okay. Okay. It's not an invertible function. To which intervals could we restrict the domain of f to make it an invertible function? From 0 to 5. From 0 to 5. Shh. 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 Yep, that's minus 5 to 0. Yep. 5 to 8, I don't think so. 5 to 8. Equal and less than 8. Less than 8. Okay. Fx x minus 5 gx. Write g of fx as an expression in terms of fx of x of x of x g of x. So we plug this here. It's gonna be x minus 5 square, x minus 5 square plus 4 plus 12. Do we have to simplify it? Because this would be so easy if we don't have to simplify. Do we have to simplify it? It's a question. X minus 5 all square minus 12. Here I got copy paste plus 4. Okay, I don't need. F is a finite function whose domain is the letter A to E. Following table lists the output for each input in F's domain. A minus 19, B 23, C, D 23, E. Answer 2 questions about the function. Okay. Build the mapping diagram for F by dragging the endpoints. Okay, so I got A minus 19, and I got B 23, and I got C 7, and I got D 23, and I got E minus 19. Nope, F is not invertible. Check. Okay, giving, you need a calculator. Giving Brian tried to evaluate, but she made a mistake. Here is her work. 9 to minus 4. Minus 4. That's 1, 1. Okay, correct. F1. That's correct, F1. It's 9 over 1 square. 9. F. That's F. G of 1 is 9. Wait. So G, if you plug minus 4, that's a minus 4. If you plug it here, it's gonna be minus 4, so it's a 9. That's a 9. 5 plus 4, it's a 9. That's a 9. 9, take it here. That's gonna be, I don't know, 81. In 9, that's gonna be 81, not 9. 3, not 1. Nope. If 1, barely evaluated, not if g minus 4, no. If 1 is 81, not 9. What do you mean? If of g9, this and this, so this is going to be plugged here. So this minus 4, it goes here. This is going to be 9. So 9, the square root of 9 is 3. 3, okay. 3, not 1. G is 3, not 1. And this is 81, not 9. Also because 3 square is 9, 9 over 9. It's choose one answer. Oh, yeah, it's not 1. It's 3. It's 3. The tables below. Oh my god, I found out that Khan Academy's questions are so tricky, man. They trick you with the tables. I don't know, with numbers. The tables, it's confusing sometimes. The table below shows some inputs and outputs of functions f and h. Okay, f h 3. So I got h 3 minus 1, got minus 1, minus 11. Nope, nope. 9 out of 10 correct. The skills leveled down 1 skill. They got me leveled down here. There's 0 skills, no change 0. So, well, that seems to be it for number 1. We did this. Next is gonna be unit 2. So bye, you guys. I'll see you in a bit. We'll do JavaScript and Python. 1 1 1 1 1 1 1 1 until I feel sleep, until I feel a bit sleepy, and I'll go to sleep. Okay, that's it for this Precalculus today. I'm not sure if I must do this again or I don't know. It was all full. You remember this was all full. Oh, I don't think so. I don't think so. I'm gonna go to unit 2.